everyone, welcome back to my YouTube channel, IBwontcrushyou, and today we are dealing with direct and inverse variation, and let's get started. Problem 1. The number of calories burned C is directly proportional to the time T in minutes of continuous rowing. A student burns 240 calories in 20 minutes, and in A write the variation equation relating C and T. So firstly, we have to remember about our sign for variation. So if our C is directly proportional to the time T in minutes, so we have to firstly write something like this. So the sign means that our C is directly proportional to time. And now we have to make an equation. So our C equals, and always when we have something directly proportional to something, we have to remember about a factor. And very often this is denoted as K and now times T. So this is almost the same, however with other sign and with factor in front of T. And now we can use our information that a student burns 240 calories in 20 minutes. So we just simply need to substitute these values into our equation. So C is calories, so calories 240 equals K. It is our factor. We are looking for it, so it stays the same, times, and in 20 minutes, and our T is in minutes, so this is it. And from this, you can solve it in your GDC solver, and K is equal to 12, so our C is 12T. In B, we have to interpret the constants of probability. So in other words, we have to interpret our 12 that we already found. So we can imagine the situation when we have, for example, 1 minute of this continuous rowing. So in 1 minute, because 12 times 1 is just 12, so we burn 12 calories. If we have 2 minutes, 12 times 2 is 24, so we burn 24 calories. So we can interpret it as 12 calories are burned per minute, and that's enough. C, using GDC, graph the function and estimate after how many minutes 600 calories will be burned. So firstly, we have to graph it, so type our function, just 12 times T, to our graph in our GDC. And your graph, your function should look like this. It's just a straight line. And here it's not necessary to draw it because we know that calories nor time, they just cannot be negative. And we have also estimate after how many minutes 600 calories will be burned. So in GSolve we have to choose X calculate, then enter Y value. So Y is 600 because our Y is C, so 600 calories, and you will see that our answer, so our T will be 50. You can also see it from our graph because we have 60 calories for 5 minutes. So if we add 1 0, so we have 600, and in time we add also 1 0 because it's directly proportional, we will have 50 minutes. Problem 2. The intensity I of light from a source varies directly with the square of the voltage V across a bulb. When V is 3, the intensity is 27 units. And in A, we have to write the equation relating I and the V. So this task is very similar to the previous one, however, here we have square of something. So we can start by simply our direct relation. So I and v, however, here squared. And now we can write I equals k, because we have to include our constant, and now times v squared. So this is our equation, and now we can find our constant by substituting our v, which is 3, and I, which is 27. So 27 equals k times 3 squared. So if you can solve it manually or using your GDC solver. However, our answer will be the same, so k is just 3. So our final equation is I equals 3v squared. In B, we have to use our GDC to graph this relationship for v from 0 to 10. So we have to type this equation into our GDC, then draw it, but we have to remember that only from 0 to 10. Your graph should be the same. And in C, we have to estimate for which value of voltage the intensity reaches 100 units. So we have to substitute 100 into our intensity, so into our I, and we are looking for V, so voltage, and you can do it simply by substituting 100 into I and typing it into solver, or by graphing it, then gsolve, and then x calculate, and we are entering y value, which is 100, and our answer is 5.77. D, explain what will happen to the intensity if the voltage doubles. And if you are familiar with this type of task, you probably already know the answer. However, we will do it step by step. So what will happen to the intensity if the voltage doubles? So simply we write 2 in front of V. So we have our 3, which is our constant, then times 2V in a bracket, and we have to remember that our V is squared. So we are doubling our V, so this whole, so 2V is squared, and now we can simplify it. So we have 3, which is our constant, then we have 4 because 2 is also to the power of 2, and then we have times V squared. And now it is very important to leave our intensity in this form. So we have 4 times 3v squared. So this is the same, and now we can see that we have 4 in front of our let's say function. So we can see that our intensity quadruples, because when we double our voltage, we have V squared, so it means that our intensity quadruples. So in order to give our final answer, we should also write intensity quadruples. Problem 3. The time t required to complete the task varies inversely with the number of people p working on it. A group of 4 people completes the task in 15 hours. And in A, write the variation equation. So here we have inverse variation. In previous exercises we had direct variation. So here the only difference is that we have to write our inverse variation in a fraction. So our t equals, and here is always the same. So our constant over our variable. So here number of people p. So it looks like this. And now to complete our equation, we have to substitute our group of 4 people and task which is completed in 15 hours. So 15 equals k over 4. So k equals 60. So we can write our equation as t equals 60 over p. And that's our equation. In B, we have to estimate how long it would take 10 people to complete the task. So we just simply need to substitute 10 into P, so our number of people. So T equals 60 over 10. So this is 6 hours. C. Explain the limitation of this model when P is very, very large. So, in order to do this point, we just need to calculate it. So, for example, we can divide our 60 by a very big number that you can type on your GDC, and you will see that our answer is very, very small. So, when our P goes to infinity, then our t goes to 0, because if we have a very big number of people, so time required to complete a task will be very small, because a lot of people will do this work, so our time, we can say, diminishes because we have a lot of labor. And we have to explain the limitation of this model when our P is very, very large. So in real life, our number of people, basically more people, doesn't really mean that they will be faster forever, because we have to include communication, space, and so on. So it's not really like this, that our number of people, which is very large, it doesn't matter that time required to complete a task will be very small. And D, what assumptions are made in this inverse variation model? So we can simply say that our model may assume that all people work at the same rate, at the same time, and no basically overhead is added with more people. So our final answer can look like this. Problem 4. The gravitational force F between two objects is inversely proportional to the square of the distance r between them. When r equals 2 meters, the force is 100 newtons. In A, write the variation equation. So here, this problem is very similar to the previous one. However, we have to include our square of the distance r. So our force equals constant over square of the distance r. So something like this, and this is our equation. And now we have to substitute our values from our comments. So we have our force 100 equals our constant over 2 squared, and then we have to simplify it. So 100 equals k over 4, and then multiply it by 4 both sides. So we have that k is 400. So our final equation is F equals 400 over r squared. And in B, we have to use our GDC to plot F as a function of r, and we are given our domain from 1 to 10. So your graph should look like this. And now we have C, estimate the distance at which the force is 25 newtons. So we can simply do it in our graph window on our GDC, Gsolve, then we have x calculate because we are looking for our r, and r is distance, and we are given our force. Force is y, so we are entering 25 into y value, and we can see that our r is -4 and 4, and we know that distance cannot be negative, so for force 25, distance is 4. In D, we have to explain what happens to the force as r firstly goes to 0 and then r goes to infinity. So you can observe that our r is in denominator, so it cannot be exactly 0. However, it can be a very small number, so you can try substituting it in your GDC. For example, r, which is 0.00001 or something like this, very small number but not 0. And you will see that f is a very big number. So if r goes to 0, then our force goes to infinity. And in the same way, now r goes to infinity. So you can try it by substituting very huge number into your r, and you will see that if r goes to infinity, our force is a very small, it's a very small number. So f goes to 0. And in E, we have to comment on whether this model is valid for very small r. So as you can see that very small r means that our force is very big. However, we have a limitation that it's not always valid for r, which is 0, because our physical forces in real life are not infinite. So it's not like 100% valid. So our final answer can look like this. Problem 5, you are given the following data relating to variables, and we have first row with x and the second row with y. And in A, use your GDC to determine if this relationship appears to be an inverse variation. So firstly, we have to recall how our relationship looks like in inverse variation. So it is simply y equals constant divided by x. So now we can try to solve for our constant by substituting x and y from a given pair. And also, to make it more easy, we can now multiply it by x, both sides. So we have x times y equals k. So our constant is just x times y. And now we can substitute our values. So I substituted all values, and as you can see, our constant is the same. However, here we have 20.1, but in approximation, this is the same. So our points there is inverse variation between them. And in B, if yes, find a suitable inverse variation model. So it's simply y equals our constant that we found, so 20 over x. So this is our inverse variation model. In C, we have to test the model for x equals 6. So simply y equals 20 divided by 6. So 20 over 6 is 3.33 to 3 significant figures. D, discuss how well your model fits the data and identify any patterns in the residuals. So as you can observe that our constant is almost the same in every case. Here we have 20.1, but this is almost the same. It's very close to our 20. So we can say that there is no clear pattern in the residuals. And so our model basically fits the data very well. So this is our answer, and the residuals, we will deal with residuals later in later topics. Here we can say that there is no clear pattern in the residuals based on our constant that here is 20, here we have 20.1, but you know this is this value is very close to 20, and here 20 and 20. Problem 6. The time t taken for a signal to travel through a wire is found to be related to the resistance R and the voltage V by a relationship involving powers. From experiments, the following data were collected, and we have in first row V, so our voltage, and in the second row we have t, so time, and in A we have to test if t varies inversely with the square of V. So basically we have the same situation as in a previous problem, however here we have to include square of V. So we just add the power to our V. And you have to remember that our t works like y, because always we are given firstly x, so in here voltage, so our v works like x, and then we are given y, so t works like y, and that's why our formula looks like this for now. And we can multiply both sides by v squared, so we have t times v squared equals k, so our constant is t times v squared. So here we have all the values substituted into our equation, and we can observe that our constant is almost the same in every case. Here we have 99.9, however we know that this value is very close to 100, so it varies. Our time varies inversely with the square of v. B, if so, write a model for the variation. So we have t equals our constant, so 100 over v squared. In C, use GDC to plot your model and data together. So we have to type our this equation, into our graph in our GDC, and then rewrite our answer on a paper. Your graph should look like this, and here you have to remember that our function is very close to our x-axis and y-axis, however it never touches them because they work like the asymptotes. So asymptotes are never touched by any function. So here is the same. They are very close. They can be almost touching a y-axis or x-axis. However, they are never touching them. D. How does the model behave outside the domain of the given data? So as you can observe, that if our V, so voltage, goes to zero, our time goes to infinity. So basically time explodes and it's not realistic. So we can write our answer like this. And you can also try it out by trying to substitute into our formula here. V0, we know that we cannot divide by 0, however we can substitute very small number, and we know that 100 divided by very small number, you can check it on your GDC by dividing 100 by a very small number that you can type. T will be very huge, so as V goes to 0, our time goes to infinity, so our time explodes. So this was the last problem from direct and inverse variation topic from chapter functions. And if you found this video helpful and useful, please leave thumbs up, subscribe to my channel, and in case of any questions, you can write them down below in comments or via my mail that is written in the description of this video. Thanks for watching!